Today I'm going to address how you can calculate the empirical formula of a given reactant using a combustion reaction. What is our experiment? Well, we're going to set something up where we have a compound that we know contains carbon, hydrogen, and oxygen, but we don't know exactly what the formula is. And we're going to take that compound and we're going to combust or burn it in excess oxygen, which in turn will produce carbon dioxide and water. If our experiment is well designed, we will have some good experimental data. We're going to know the starting amount in grams of our mystery compound that contains carbon, hydrogen, and oxygen. And we're also going to be careful when we collect our gram amounts of carbon dioxide and water. And from this data, from these three pieces of data, we can actually calculate the empirical formula of this mystery compound of ours. We should think about what our chemical equation is going to look like. So in terms of our mystery compound, we know it has carbon, hydrogen, and oxygen, but we don't know in what ratio those three elements are combining. We're going to add excess oxygen, and we're going to produce carbon dioxide and water. Now, please ignore the stoichiometric coefficients I have here because they don't make any sense in this current situation. You could, however, perhaps work backwards and practice your balancing equation skills by figuring out what the formula of CHO here is going to be. But that's not our charge, actually. Our charge is to use the data we collect to get at the empirical formula. And a typical setup is going to be to take some compound, in this case ethanol, expose it to excess oxygen, and then collect our H2O and our CO2, and this is how it's going to work. This is, if you were in the lab, the kind of experiment that you would set up in order to achieve your determination of the empirical formula of your compound. Let's imagine we did this experiment and we started with 12.915 grams of our CHO compound. And then at the end, we collected 18.942 grams of carbon dioxide and 7.749 grams of water. Our first charge is to find gram quantities of carbon, hydrogen, and oxygen. The way that we need to go about this is to tackle carbon and hydrogen first. Now, if you see grams of carbon dioxide, you have to think about, well, how am I going to get at the gram quantity of just carbon? And the way to do that is basically a three-step process. You start from your grams of CO2, you use molar mass of carbon dioxide to get moles of CO2, you then use the mole-to-mole ratio of carbon to carbon dioxide to get moles of carbon, and then use the molar mass of carbon to get grams of carbon. That's step one. You repeat this process for water. So you take your grams of H2O, you convert that to moles of H2O. You note that there's a 2-to-1 ratio, 2 moles of hydrogen for every 1 mole of H2O. This is important. Then finally, you can take your moles of hydrogen and get grams of hydrogen. A slightly trickier part comes in when we have to figure out how many grams of oxygen were in our original compound. And the way we can think about this is in terms of the law of conservation of mass. We know that we started out with 12.915 grams of a compound that is composed solely of carbon, hydrogen, and oxygen. We also know that we collected a certain amount of carbon and a certain amount of hydrogen. In fact, we just figured out the path to calculate those two amounts. It follows that the grams of oxygen will equal the grams of our unknown compound, from which we will subtract the grams of carbon and the grams of hydrogen that we just calculated. You can think of it as a zero-sum game. Whatever is left over after we subtract carbon and hydrogen must, in fact, be oxygen. Now we are really close to getting where we want to go. We have grams of carbon, hydrogen, and oxygen, and we can take each of those elements, convert those to moles, and then do the following steps to get at the empirical formula. Here we see the solution to the problem, and we're going to follow exactly all the steps that have just been discussed. So note, in this first case, we're going to get grams of carbon. And if we were to look carefully, we would notice that everything cancels appropriately. Moles of CO2 will cancel. We'll then use our mole-to-mole ratio to get moles of carbon, and we'll use our molar mass of carbon to give us our grams of carbon. So that's a good start. We repeat this process for hydrogen, and then we do this conservation of mass approach to figuring out how much oxygen we have. We take our 12.915 grams of starting material, and we subtract the combined masses that we just calculated of carbon and hydrogen, and that will give us the amount of oxygen in our starting compound. Now we simply apply the principles that we have used, that you have seen before, to calculate an empirical formula. And that involves taking the gram quantities of each element and converting it to moles. Now what usually happens in a problem like this is you get fractional amounts, and you need to turn them into whole number amounts. You may recall that you do that by dividing by the smallest number, in this case 0.4299. And in this case, we don't have to do a lot of manipulation. We get this ratio that you see here of 1 mole carbon, 2 moles hydrogen, 1 mole oxygen, which in turn gives us a formula of CH2O. So we've done it. We solved the problem. It's a bit of work, but it's concepts that you're familiar with. It's just a question of getting to know them and applying them in the right order. In that spirit, here is a recap of what you have to do on a slightly more reduced level, let's say. I would say for part 1, it's important to recognize conceptually that you really need to get from grams of compound to grams of element. So this is step A. And the way to do that, as just discussed, is to go from grams of compound to moles of compound to moles of element to grams of element. Then we have to use that data to figure out any remaining element that we can't calculate in that manner. We just saw, in order to get grams of oxygen, we can take the grams of starting material, subtract the grams of what we just calculated of our known elements, and we'll get the grams of that remaining element. Finally, in part 2, we will take all these gram amounts, convert them to moles, and then we'll basically derive our empirical formula in the form of fractional numbers. That's part B here. And then finally in C, we'll multiply those fractions or manipulate them in whatever way we need to in order to get whole numbers. So actually, in fact, once we get the fractional numbers, we divide by the smallest fractional number, and then if we need to, we multiply those numbers out until we get whole numbers. And then, by George, you have done it. You have calculated your empirical formula.